in one galaxy. And then when you say 2 trillion galaxies, that's, I challenge anyone to be able to picture that. But it is the reality that we've observed. We haven't counted all 2 trillion, by the way. We have a thing called the Sloan Digital Sky Survey, which maps the positions of galaxies. So you know how much of the sky you've surveyed, and you know how many galaxies you've counted, and then you can spread that across the wider universe, and you get this picture of a vast and possibly infinite universe. I mean, we know that the universe, or very strongly suspect that the universe is much bigger than the piece we can see. So we have good reason to think that's the case. Whether it's infinite or not is another question. And then that goes to can you picture infinity? Well, no one can picture infinity. There's a weird thing as well about, we say the universe began 13.8 billion years ago. So that's a measurement, because we can measure the speed that all the galaxies are flying away from us, essentially. And then you can run time backwards, if you like, to find out when they were all on top of each other. And so it's quite a simple measurement, and we've done that. So we say the universe began 13.8 billion years ago. But actually, all we know really was the universe was very hot and very dense at that time. And we have some theories that the universe was in existence before that, and perhaps some sort of circumstantial evidence. And that means that actually the universe could have always been there, eternal. And when I talk to people sometimes, some people get upset about that. Some people would rather it had a beginning. And the idea that it might have been around forever is more frightening somehow than the fact that it began. And it's interesting the way that people's minds work. What terrifies you the most, an eternal universe or a finite universe? Those theories are back in vogue. Some of those theories are back in vogue again. So yes, some of them say that there's a cycling universe. So the Big Bang is an event when space gets very hot and very dense and filled with particles. And that may happen again. Or some of the other theories, there's a theory called eternal inflation, which is a theory that, and it's actually the most popular theory, I think, at the moment, for what happened, for why the Big Bang is the way that it is. Because it's got some very special features, the Big Bang, which we could talk about. But inflation is the idea that space-time was around before the Big Bang, and it was expanding extremely fast. And there was doubling in size in the most popular of these theories every 10 to the minus 37 seconds, which is 0.00000 with 37 noughts, 1 of a second. So it's an unimaginably fast expansion. And then the idea is that draws to a close, so it quite naturally sort of dies away and the expansion slows down. And all the energy that was causing that expansion sort of gets dumped into space and heats it up and makes particles, and that's what we call the Big Bang. And those theories, the slight extension to those, say that slowing down just happens in little patches. So most of the universe, the overwhelming majority of the universe, is still inflating at that insane sort of speed, and just little patches stop and they're Big Bangs. So you get multiple universes, a multiverse. It's called the inflationary multiverse, and we are in one of those bubbles, and that's one of the more popular theories.
Enrico Fermi is one of the great physicists, legendary Italian physicist, who laid many of the foundations of modern 20th century physics, so-called Fermi-Dirac statistics and all sorts of things. If you do a degree in physics, then you will spend a lot of time revising equations and theories that Fermi did. One of the great legends. The Fermi paradox is it's probably the thing he spent least time on, actually. It's almost one throwaway remark that he delivered. and the question is, where are they? By they, I mean aliens. The heart of the Fermi paradox is this. We know that we live in a big old galaxy, in a big old universe. And let's, for the purposes of this discussion, confine ourselves to the Milky Way galaxy. The Milky Way galaxy, we now know, has something like 400 billion suns. And we now know that most of those suns have planetary systems around them. So trillions of planets. The galaxy's been around for pretty much the age of the universe, 10 billion years plus. And so there's a lot of real estate, and there's been plenty of time for civilizations to develop in the galaxy. The Fermi paradox, at its heart, is that the statement that notwithstanding the fact that there have been billions of years on billions of worlds for civilizations to arise, we see no evidence of any of them in the galaxy at all. So the paradox is why? It's a paradox. And I think it's a very good question. It's an extremely good question. And there can be many answers. And the great fun, or I would say the intellectual value of the Fermi paradox, so if we accept that we haven't seen any, so let's accept that. Let's accept that there isn't a UFO sat in some warehouse in Roswell or something like that. Let's accept that we haven't seen any. Let's accept, we have to accept the picture that I've just given you about the Milky Way galaxy and its age, because that's a measurement, so we know that. The question is then, why? How do we resolve these apparent contradictions and paradoxes? So one answer to the Fermi paradox, this is the idea that we don't seem to see anyone, is that no one ever evolved. Right? So life didn't get complex. Why might we think that? Well, what did we need to produce our civilization on this planet? Well, on this planet, one thing we needed was time. We have good evidence that life was present on this planet 3.8 billion years ago, perhaps even earlier. The planet is 4.5 billion years old. So we know, as a matter of fact, as an observation on this planet, that life was present 3.8 billion years ago, but it took 3.8 billion years, give or take a few tens of thousands of years, to go from the origin of life to a civilization. Let's say from cell to civilization. 4 billion years. That's 1/3 of the age of the universe. So a possible answer to the Fermi paradox, the question of why there are no civilizations, is because the Earth is pretty much unique in the Milky Way galaxy in that it was stable enough, the climate, the conditions on Earth were stable enough for long enough for life to go from cell to civilization. If you think about it, that's a big ask. What I'm saying is, on this planet, an unbroken chain of life existed for almost 4 billion years, notwithstanding the fact that we live in a violent universe. The sun must have been stable enough for long enough. We know the output of the sun has changed over those billions of years, but it's not changed so radically that it managed to erase, destroy life on Earth. We know that we live in a violent universe. We know there are supernova explosions all over the place. It turns out that there have been no stars massive enough to explode as a supernova in a way that would damage life on Earth or erase life on Earth in this vicinity for 4 billion years. We know that nothing has happened. We know that there have been impacts on the Earth, right? We know that the famous impact that wipes out the large dinosaurs, there's been no impact big enough to destroy the unbroken chain or break the unbroken chain of life for 4 billion years. So maybe it's the case that whilst there are billions of planets which may have liquid water on the surface, may have oceans that can support life, it may be that none of those planets in the Milky Way galaxy have been stable enough for long enough to produce a civilization. So that would be a property of the planet itself, the so-called rare Earth hypothesis. Actually, I should say it's a property of the solar system. It's not really just a property of the planet. It's a property of the parent star. You could ask the question, well, if it was a binary system, for example, a binary star system, many stars are binary star systems. Is it possible to have a planet with a stable climate, stable enough orbit in a binary star system to support an unbroken chain of life for 4 billion years? Perhaps not. When we talk about rare Earth, I think I would like to talk about rare solar system. Another possibility with the Fermi paradox is that it's not a paradox, they are here. So there are intelligent civilizations out there and they are present in the solar system. It's possible. Let's think, for example, what such an intelligence might look like. Well, who knows? They could have sent nano machines to our solar system. There could be probes all over the place in the solar system, but if they're the size of an iPhone, then we'd have no way of detecting them. So it could be the technology of a sufficiently advanced alien species, a civilization, is so beyond anything we can comprehend or detect that we haven't seen it, and we've been fooled into thinking that there are no advanced civilizations in the galaxy. And that's certainly entirely possible. Another possibility, another possible resolution to the Fermi paradox is just that the galaxy is so big. The distances between stars are so great that if you imagine there's another civilization, let's say on the other side of our galaxy, let's say 20 million, 30 million, 40 million light years away, even if they had the most powerful radio transmitters you could imagine, or even if they'd spread out to neighboring solar systems, then it may just be that the distances are so great that the signals are diluted, that we can't detect them because they're too weak, or that it's just very, very, very difficult in an engineering sense to build interstellar spacecraft. Now, perhaps you can build a spacecraft that can hop a few light years away to the nearby solar system, 4 light years in our case to Alpha Centauri, but you can't build spacecraft that can traverse a galaxy. Yeah, it's a remarkable instrument. I mean, you think of the predecessor, which is the Hubble Space Telescope. I think it's almost impossible to imagine a world without that. Even if you don't know the images that we're familiar with of the universe, many of them, the spectacular galaxies and star-forming regions, they're from Hubble. But the Webb is a significant step forward. And technically, one of the most important things is it can see what we call longer wavelength light, or infrared light. And that's important because if you think about, we want to see the first galaxies forming. So we want to understand how the first stars and galaxies formed in the universe. And so what you do is you look far out into the universe. And because light travels quite slowly across cosmic distances, let's say you have a galaxy that's the most distant one you can see with the naked eye is about 2 million light years away. So that means that the light has been traveling for 2 million years to reach us. And it's a remarkable thing, actually, to think when you look, it's called the Andromeda Galaxy. And if you know where you're looking, you can just catch it out of the corner of your eye. If you think about it, you're seeing that as it was 2 million years ago. It's remarkable. I mean, it began its journey before we had evolved on Earth. So in the time it took, and that's the nearest neighboring galaxy, the Webb looks so far out that it's capturing light that's been traveling for over 13 billion years. But the universe has been expanding. And so the light has been stretching. And so for the most distant galaxies, we're looking back in time almost to the Big Bang. Then the Hubble was not sensitive to that light. So that the Webb can see the formation of the first galaxies. It's essentially looking all the way back to very close to the beginning of time. And that's very important because we're not entirely sure exactly how those first galaxies formed. Well, we almost can. It's not the Webb telescope. There's something called the cosmic microwave background radiation, which is light that was emitted in the universe. And it's a very precise number. It's 380,000 years after the Big Bang, which is not very long at all. Right? The universe is 13.8 billion years old. So we can see that. It's microwaves because it's been stretched so much by the expansion of the universe. Going back, the problem with light is that in those earliest times, the universe was so hot and so dense that light couldn't travel through it. So it was opaque. So you can't use light to go back earlier than that. But what we can potentially do, not yet, we're not good enough yet, but the technology we use now to detect colliding black holes, which is another remarkable thing, but I'll leave that one aside for now. But we have the technology to do that. And that technology possibly could allow us to probe right back to this thing, the Big Bang. And again, whether or not that's the origin of time, we can talk about as well. Well, so this, again, I think in cosmology, and I say this in the show as well, it's one of the most challenging subjects because at one level it makes us feel very, very small and insignificant. And it's true, physically. I mean, the Earth is one planet around one star amongst 400 billion stars in one galaxy amongst 2 trillion galaxies in the part of the universe